This is the 14th video in my series on alternating current. In this video, I'm going to take a look at voltage, current, and instantaneous power in a purely inductive circuit in both the time and the phasor domains. You'll find this topic along with my other courses entitled Basic Fundamentals of AC Circuit Analysis. You can find this course, as well as my others, on this web address. Inductors do not behave the same as resistors, whereas resistors simply oppose the flow of electrons through them by dropping the voltage directly proportional to the current. Inductors oppose changes in the current through them by dropping the voltage directly proportional to the rate of change of current. This induced voltage is always such a polarity as to maintain the current in its present value. That is, if the current is increasing in magnitude, the induced voltage will push against the electron flow. If the current is decreasing, the polarity will reverse and push with the electron flow to oppose this decrease. This opposition to current change is called reactance rather than resistance. Expressed mathematically, the relationship between voltage dropped across the inductor and the rate of change of current through the inductor is as this formula indicates. The voltage is equal to minus L di by dt. The minus sign indicates that the voltage is opposing the change of current flow. The expression di by dt is one from calculus, meaning the same thing as delta I over delta t as delta goes to zero. So it's really the change of current over the change of time. So this meaning the rate of change of instantaneous current over time in amps per second. The inductance L is in henries, and the instantaneous voltage, of course, is in volts. If we plot the current and voltage for this simple circuit, it would look something like this. The circuit has an AC source of voltage, ET, acting on an inductor with an inductance of L. Remember, the voltage drop across the inductor is a reaction against the change in current through it. Therefore, the instantaneous voltage is zero whenever the instantaneous current is at a peak, zero change, or level slope on the current sine wave. And the instantaneous voltage is at a peak whenever the instantaneous current is at a maximum change, the point of steepest slopes on the current wave, and that is where it crosses the zero line. This results in a voltage that is 90 degrees out of phase with the current wave. Looking at the graph, the voltage wave seems to have a head start on the current wave. The voltage leads the current, and the current lags behind the voltage. The phasors would look like this, where the voltage phasor would be leading the current phasor. Remember now that the phase rotation is counterclockwise. Let's consider for a moment a pure inductive load in an AC circuit. Because instantaneous power is the product of the instantaneous voltage and the instantaneous current, that is P equals I times E, the power equals zero whenever the instantaneous current or voltage is zero. Whenever the instantaneous current and voltage are both positive, above the line, the power is positive. As with resistors, the power is also positive when the instantaneous current and voltages are both negative below the line. However, because the current and voltage waves are 90 degrees out of phase, there are times when one is positive while the other is negative, resulting in equally frequent occurrences of negative instantaneous power. Notice on the graph here that the power goes from 0 to a maximum, back through 0, up to a positive maximum, back to 0, down to a negative maximum as the current and the voltages swing through their positive and negative crests. You'll notice that when the current slope is 0 at the crest of its wave, the voltage is just crossing the 0 line, so voltage is 0, hence power is 0, and indeed that's what the green line shows here. Again, where the current slope is equal to a maximum, in other words, its slope is at a maximum slope where it's crossing 0, voltage is a maximum, but because current is a 0 at this point, so is the power 0. Another 0 point for the power is where the current slope may be a maximum and the voltage may be a maximum, but the current slope or the current is 0, so the power is 0. And where the current slope is 0 and the voltage is 0, then of course we have 0 power. This video is part of my Electrical Technical Information series. In this series, I'll be covering essential topics to help you understand electrical systems. Be sure and stay tuned, as I will also, from time to time, be reviewing electrical products that, in my opinion, are worthy of paying attention to. This address will give you access to the supplier of the aforementioned type products. It is also a connection to obtain a free copy of my 24-page 3-phase transformer workbook, which will serve as a quick reference and reminder of technical calculations that you may need. This address, of course, is case sensitive. I'll spell it out and make sure that you have it right. Everything up to the first number is lowercase. That is lowercase https://bit.ly/3, then uppercase U, uppercase G, a lowercase j, uppercase B, uppercase I, and lowercase g. One of those amazing and versatile products is the 𝐃𝐈𝐒𝐂𝐋𝐀 Delta Pro Ultra, which can be modified to suit any homeowner's needs, operating virtually silent, and when paired with the 𝐃𝐈𝐒𝐂 Smart Home Panel 2 is extremely versatile. The 𝐃𝐈𝐒𝐂 Home Panel 2 ties any and all of your standby power equipment together and will control them efficiently. It will even control your connection to the utility grid to make sure you're only using the least expensive power, switching to your standby power during those expensive time of use rates. In order to view the full range of 𝐃𝐈𝐒𝐂's products and obtain a free copy of my 3-phase transformer workbook, check into this web address and simply provide your email address, which will guide you to browse the full extent of their products. There is no cost or commitment for viewing, and by providing your email address, it will allow me to keep you posted on future videos, courses, and 𝐃𝐈𝐒𝐂 products.